Precalculus students, welcome to your 11.2 notes. Today we're going to take a look at finding limits of functions that have to do a little more work than we've done in the last section, but I think for the most part it'll be pretty logical type problems, things that would make sense to you. So let's take a look at it. Let's jump right into it. Number one, dividing out technique is what we're going to use. So the limit as x approaches 4 of the function that's given to you. Now the problem would be if we plugged in 4, we'd have division by 0. And so clearly that's going to be an issue. But if you take a look at that denominator, we could factor that to be x minus 4 times x plus 3. And then we could cancel those two terms and basically consider it to be the limit as x approaches 4 of 1 over x plus 3. And that we can actually just plug in directly. So we can use substitution and we'd get 1/7. All right, now that one would actually be a hole in the graph. If you wanted to graph that on your calculator, you could see that you'd have a hole there, but the limit still exists because it's approaching 1/7 both from the left and the right. Okay, the next one we have here may test your factoring skills just a little bit, but x cubed plus 27, if you remember the cubic factoring pattern, that would be x plus 3 times x squared minus 3x plus 9. If you don't remember how to factor cubes, you might want to just look that up. You can look it up in your textbook, your old notes, or just go online and look for the factoring of cubes. You'll find that pretty quickly. And you'll notice the x plus 3's cancel. And now we can evaluate because basically what we have is a limit as x approaches -3. And I didn't really mention this when I started writing it, but the reason we have to simplify this first is, again, we'd have division by 0 if we plugged in -3 right here. But once we cancel out the x plus 3 terms, you can see we'd have 9 minus 9 9 plus 9 plus 9, so 27 is our limit. All right, so just a matter of plugging in -3. Now again, you couldn't just do that from the beginning. Algebraically, you'd have an issue. But you could do that by graphing it and taking a look at it. That way, that would definitely work. All right, so let's look at the next slide. We're going to use a different method here. And the name may look kind of funny, rationalizing the numerator. We're used to seeing, rationalize the denominator. But again, we run into the situation of you can't just directly substitute. Like if you plug in 0 for x right here, you'd have a bit of a problem. So we're going to use rationalizing the numerator. So what I'm going to do is multiply by the conjugate of the numerator. Again, these problems they're basically set up for this to work. This technique doesn't work on every problem or anything like that, but any of them that say to use this method, it'll be there for you, and we'll set some up to work this way. So here we go. We're going to go ahead and multiply, and remember you've got to FOIL that thing. So our numerator, we're going to have x plus 4 minus 4 basically is what we end up there. That's the square root of x plus 4 times square root of x plus 4 gives us x plus 4. Middle terms cancel, and then -2 times +2 gives us the -4. The denominator for now, I'm just going to leave it in the factored form. Typically that's the way we'd want to do that. We can't do much with x times x squared of x plus 4 and so on. Anyway, so it's honestly just better to leave it in the factored form, because look what happens here. Plus 4 minus 4, goodbye. And now we just have an x divided by an x, and actually, hey, well, x divided by x, let's get rid of that. That's just 1. And so what we've got is the limit as x approaches 0 of 1 over, and then we have this denominator. It's a little bit of a weird denominator, square root of x plus 4 plus 2. But the nice thing is this, when you plug in 0, square root of 4 is 2, 2 plus 2 is 4, so your limit is 1/4. So that's the rationalizing the numerator technique. Let's try that one again. Same technique with some new numbers basically, but same kind of problem. So again, we'll use the conjugate. So x plus 9, square root of x plus 9 plus 3. We're going to multiply that both numerator and denominator. And that'll give us the limit as x approaches 0 of, and then our numerator would be square root of x plus 9 times square root of x plus 9, which is x plus 9. Negative 3 times 3 gives us a minus 9, and there's no middle term, of course, because this one would be minus, the other would be plus. They cancel. It's a difference of perfect squares situation, essentially. Just slight variation from the way we're used to seeing it. And then again, keep the denominator in the factored form. It'll definitely be, it'll pay off. And then I see I have a plus 9 and a minus 9. X divided by x, that's just 1. And so our numerator is 1. Our denominator is the square root of x plus 9 plus 3. And this would be square root of 9, which is 3 plus 3. So our limit, of course, is 1/6. And again, I didn't mention this at the beginning of the problem, but you can't use direct substitution on this one. For the same reason as all the others we've seen so far in this lesson, is that you'd get division by 0. We don't like that. As we move to the next slide, we're going to use technology, specifically graphing calculators, to evaluate limits, and we could have done that on others as well, as I've talked about. But I want to show you what it looks like with a problem like this. So we're going to start by graphing the function x squared minus 4x minus 5 over x plus 1. Now, technically I could just go to the graph and use that if I wanted, but I'm actually going to do it a different way. I'm going to go to the table, and what we're looking for is as x approaches -1. Now you'll notice on the table that -1, it tells me there's an error right there. You might be able to see, and you probably can see, the pattern. I'm going to go a little bit more in depth on that though. I'm going to go to second, and it's above window, it says table set, and I'm going to have my table start at -1, and I'm going to change the delta table, maybe like 0.01 is probably good. That's going to allow me to see 1/100th steps basically. So now I'll go back to my table, second in table, and I'm going to scroll up just a little bit. This will give us a really good picture of what exactly we're talking about when we say the left and right hand limits are the same. So I can see as we approach from the left, we're at 6.04, 03, 02, 01, and then it skips, it says error, and then 599, 598. I think you guys are kind of getting the idea probably that the limit here would have to be -6. In other words, you're kind of filling in the blank. Look at the pattern and figure out what number would obviously be there. All right, let's do why don't you guys do this second problem, the 1 minus cosine of x over x. Do the second problem on your own and see if your answer agrees with me. All right, you can see my work now. Here is the table. And this one, again, had to use a little bit of a judgment call and say, okay, well, what's going to be here? Now, one technique you could use is, and we'll look at this on the next example actually, sometimes it's pretty obvious, like -0.005 to +0.005. The number in between, of course, is going to be 0. Sometimes you run into a situation, though, where the number in between isn't quite as obvious. We're going to run into that on the next one. So let's go ahead and graph x plus 1 to the 1 over x power. It's kind of an interesting little graph. If you want to look at the actual graph, you can. Truthfully, what we're more interested in is again the table, because we want to see the limit as it approaches 0. I think I actually have a pretty good table set already, so I'm going to go ahead and go take a look at that table. And here are the numbers. Now, these numbers may not mean that much to you, but here's what we do in this situation where we just have to essentially approximate, is we're going to take the two numbers closest. So I've got like 2.732 and 2.7048, and I'm going to divide those numbers. I'm going to add them and divide by 2. Now when I do that, I get about 2.718. I'm double checking that number real quick. Yeah, 2.718. Now, some of you may recognize this number, 2.718. It's E. Our old friend comes back. Really interesting way to find E. As we move forward here, we're going to talk about something that I hinted at both earlier in this lesson and in the first lesson, actually, but we haven't really seen the notation. But when you see this, the notation you see here, limit as x approaches, and it looks like c negative or something like that. We're talking about right over here. Okay, what that means is it's a left-hand limit. What is the graph approaching from the left? When you see the limit of c plus, basically, that's the limit as you approach from the right. So we could just say it as the limit as x approaches c from the left and the limit as x approaches c from the right of the function, and then you get these values L1 and L2. Now here's the deal, and we talked about this again in the previous lesson, but a function has a limit only if the left and right hand limits agree. In other words, if they're converging to the same point. All right, so let's take a look at both left and right hand limits and see what we come up with on this next one. So we have the limit as x approaches 0 of the absolute value of x divided by 5x. I think it's worth taking a minute to kind of sketch what this graph would look like. It's kind of an interesting graph. On the right hand side, we'd be at 1/5. On the left, we'd be at negative 1/5. So here's what I'm seeing. The limit as x approaches 0 from the left of our function, that's this side. So as we approach 0, moving to the right, we would see that it would be at negative 1/5. My limit from the right, though, so my limit as x approaches 0 from the right of this function is positive 1/5. This is a mean girl situation, folks. The limit does not exist. And you can use this DNE abbreviation if you would like. Now, why doesn't the limit exist? Well, left and right behaviors have to agree. And in this case, they do not. All right, so let's look at the next one. We have a little piecewise function here. The limit as x approaches 2. So let's do the limit as x approaches 2 from the left of our function, and we would get, that would be this rule. So as we approach 2, it would be 5. If we approach from the right, we'd be switching rules to this second rule. And in that case, we'd have negative 1/2 times 2, so that's negative 1 plus 6. So it's 5. So our limit as x approaches 2 of this function exists. It's 5. So again, if the left limit and the right limit agree, you have a limit. If they don't, well, then you don't. All right, we have one topic to look at today, the difference quotient. We're going to do 3 different problems on this. They're all a little bit different in the way they work. So the difference quotient, and this may look familiar to you because we actually saw it earlier this year. The limit as h approaches 0 of f of x plus h minus f of x over h, although it has been a while. All right, so here's what I'm going to advise you to do. First of all, before you try plugging things into this difference quotient, let's evaluate f of x plus h. And sometimes people get a little sloppy with the basics on these problems, and I think by writing it down, it really helps. So there's f of x plus h. Now, all that means is wherever there was an x, you write x plus h. Now, if you want to get a little more advanced with this, you could go ahead and change this to x squared plus 2xh plus h squared, and you'd still have that plus 3 at the end. That would be fine too. All right, so let's evaluate our limit. We just simplified f of x plus h. That's x squared plus 2xh plus h squared plus 3 minus the original function f of x. So that's x squared plus 3. Notice the parentheses around that. All divided by h. So we're trying to, again, evaluate the limit as h approaches 0 of that function. Now, we can't just plug in 0 right here because we'd have division by 0, but take a look at this. X squared cancel each other out. 3 and 3 cancel each other out. So what we have then in the numerator, you'll notice I only have h terms left, and I'm going to go ahead and factor out an h. And I think you may be seeing, oh, that's an h. You may be seeing the reason I wanted to go ahead and factor out the h is because it cancels, and so we're left with the limit as h approaches 0 of 2x plus h. All that means is plug in 0 for h. Well, 2x plus 0 is 2x. There's your first one. On the next two, we kind of up the algebra just a little bit. Have to use a little bit more complex techniques perhaps. But again, I want to start by finding f of x plus h. We can't simplify this one like we could the last one quite as much, but I could definitely write that, and that may be helpful to us. So f of x plus h is the square root of x plus h minus 2, and I decided I'm going to go ahead and write down here because I'm going to need a little more space. So square root of x plus h minus 2 minus the original function, which was the square root of x minus 2, all over h. And again, you'll see this every time with difference product or difference quotient, excuse me. You can't just plug in 0 for h. You got to do something first. So what we're going to do is actually a technique that we used earlier in this lesson, which is rationalizing the numerator. I'm going to use a conjugate here, and this technique will really help because it allows us to eliminate lots of things you'll see as we move forward. All right, so our numerator, after we multiply these two things together, is just simply x plus h minus 2 minus x minus 2. Difference of perfect squares situation. We set it up. The denominator, it's ugly, but I'm going to leave it factored. Don't try to combine these things. There's no reason to do that. It's just going to make your life really difficult. And here's what's nice about these problems. You'll notice that in the numerators, all the terms that don't have h's, if we're doing this right, they should cancel. And you can see now all I have left in the numerator is just simply an h, which can cancel with this h down here. So I've got 1 over the square root of x plus h minus 2 plus the square root of x minus 2. And I know that that doesn't look real pretty, but here's what we really like about this. You can plug in 0 for h right now, and you'll have 1 over, and you'll have 2 times the square root of x minus 2, because you've just got simply square root of x minus 2 plus square root of x minus 2. And folks, that's our limit. That's the difference quotient right there. Now as we move forward, we have another name for this. It's called the derivative. Has some pretty cool applications in calculus. But for now, we can just go with that. All right, we have one more. It's another one where the algebra can be a bit tricky. So f of x plus h, I'm going to start this one the same way. And I'm just going to do a quick substitution. So instead of x, I write x plus h, and hopefully write it legibly. And then minus 3 is still there. So let's go ahead and plug everything in. Our limit as h approaches 0 of f of x plus h, that's 1 over x plus h minus 3, minus the original function, 1 over x minus 3, all over h. All right, that looks a little scary. I get that. It is. There's no way around that. But let's just do this one piece at a time. Common denominator up here. So it's going to be the product of x plus h minus 3 and x minus 3. So I need to multiply both of those terms. You've done this many times, probably in more complex situations than this even, where we can just get a common denominator. And it would look something like this, x plus h minus 3 and x minus 3. So remember, that's just the numerator of this thing, and the whole thing is over h. Or maybe you'd prefer to think of that as h over 1. And I'll show you why that could be beneficial in a moment. Now here's what I see up here, the very top numerator, x minus x, -3 minus -3. And all I'm left with is a negative h. Okay, so this is the limit as h approaches 0. So again, that numerator is negative h. Now when you think about multiplying by or dividing by h, that's the same as multiplying by 1 over h. So I'm going to put that right there. I'm just going to move it to the denominator. And then all of a sudden we can see, well, those h's are going to cancel. So all we have here is the limit as h approaches 0 of -1 over x plus h minus 3 times x minus 3. And I know you guys haven't done many of these problems, but that moment when the h cancels is hugely important, because now I can plug in 0 for h. I can just do a direct substitution. Numerator is going to be -1. Denominator is x minus 3 times x minus 3. I'm just going to write it as x minus 3 quantity squared. Folks, that's our difference quotient, and that is our limit as h approaches 0. Okay. Again, we'll get more into this topic. The algebra can be a bit tedious, and it's possible that I lost some of you at some step along the way on any of these last 3. If that's the case, just bring your questions in to class, and we'll look at those together so we can get you rolling. You guys have a spectacular day.